Hello, everyone. In today's session, I want to go over integration by parts, which is an important, topic in integration. So uh, let's do that. So what do we mean by integration by part? You know that, okay, let me check. Okay. You know that in differentiation, when I differentiate a product of two functions that are functions of x, we say the derivative of u times v. You remember that some people tell you the first times the derivative of the second plus the second times the derivative of the first. And some people say the derivative of the first times the second plus the, it doesn't really matter. So it's really u dv plus v du. Meaning if I have two products and I want to see how their product change with respect to x, I say, okay, let's assume the first one is stable, is constant, and then I see how the second one changes, and then fix the second and see how the first one changes, and then add them together, which is common sense, right? Now, if I integrate that equation with moving things around. So first of all, for example, I can say u dv, just simple algebra, equals duv minus v du. And then if I integrate these three terms according to to what you learn is that the integral of the derivative, these are inverse operators, they cancel each other, and you get the integral of u dv equals u times v minus the integral of v du. And that's basically the essence of integration by parts. Now, how do we do that? Let's take an example and see for ourselves. Suppose I want to integrate x times natural log of x dx. How do I decide which one I use as u and which one as use as dv? It's very easy. Not always, but most of the time. And if it's not easy, I will tell you how we can circumvent that. So if I have a function like that or an integral like that, look at both and see which one is easier to integrate and which one is easier to differentiate. Now, I know, but I'm going to say I don't know how to integrate natural log of x, but it's easily differentiable, right? And it's easy to integrate x dx. So I'm going to say let u, this is the one that would be differentiated, be natural log of x. And the one that I can integrate, which is x dx and dv equals x dx. Then I have to find the other. So I have u, here is u. I have dv, here is dv. So I need to find du and I need to find v to have all four components. So du, we know that it's 1 over x dx, or you can write it as dx over x. And v is the integral of x, which is x squared over 2. Don't say plus a constant. We'll see that, and we'll keep it till the end. So now this integral becomes, if I substitute, this is u. I'm sorry, this is u. So let's write this as u. And then the other one is dv. So I know the answer is u times v, which is x squared natural log of x over 2 minus the integral of v du. V is x squared over 2, and v, we said du, and du is dx over x. So the first part stays the same. Let's simplify the second one. I have the square with the x, and this is negative. You can take the 1/2 out or leave it. It doesn't really matter. The integral of x dx. I know the integral of x dx. We already did it. It's x squared over 2. So the final answer becomes x squared natural log of x over 2 minus x squared over 2. And there is a 1/2, so x squared over 4 plus a constant. And that's basically how we do it. Now, you will see that sometimes, especially if in some integrals, I have to repeat this operation 2 or 3 times. Then we have like a tabular way of doing it. How is that? You pick the function that you will derive and place it on the left, and the function you want to integrate and place it on the right. Now, I would put natural log of x here, and x dx here, just x, right? We write x. And then I say, okay, if I differentiate that, I get 1 over x. If I integrate that, I get x squared over 2. And I don't need to do anything after that. Then you would say the integral becomes this times that. And if I have another differentiation and another integration, I would say this times the next one, but negative, next positive, next negative. I keep alternating the signs. But if I have to stop at one step, I would say minus the integral of those who are at the same level. Maybe now it's not clear, it will become much clearer later. So basically, when I'm going to say, I would say equal this times that, which is x squared natural log of x over 2 minus the integral x squared over x is x, so x over 2 dx. And I get the same exact equation. You see, x squared natural log of x over 2 minus 1/2 integral of x dx. Let's take another example that would make that much clearer. Let me try to see if I have, maybe this page has a lot of examples. So I'm going to pick one of them. Okay, so this one says integrate x³. Is it? Oh, it's x. I picked the wrong one or what? No, it wasn't x. Yeah, x³ times e to the power of 2x dx. x³ times that. And you say, oh, do you see here that if I try to do that with the traditional way, I will have to do this substitution multiple times? So that would be a very good candidate to the tabular form. And again, how you ask yourself, oh, if one of these two functions by repeated differentiation will disappear, I would make it u. You say, what do you mean disappear? I would say if you keep differentiating e to the 2x, you will get 2e to the 2x, 4e to the 2x, and you can see that it never ends. But if you differentiate x³, it will be something 3x squared, and then 6x, and then 6, and then 0. Oh, 0, meaning it will vanish. So that is a perfect candidate for being the differentiating part. So I would differentiate x³ and I will integrate e to the 2x dx. Let's do that step by step. On the left-hand side, the x³ becomes 3x squared, then 6x, then 6, then 0. So I have to integrate that multiple times. Well, the integral of an e function is so easy, right? You take the same function and you divide it by the derivative of the exponent. The derivative of the exponent is 2. So it's 1/2 e to the 2x. 1/4 e to the 2x. 1/8 e to the 2x. 1/16 e to the 2x. See how easy it is? Very simple. Now I'm going to say first times second positive, second times third negative, third times fourth positive, fourth times fifth negative. And you see how easy and how fast we can do it? So that integral becomes 1/2 x³ e to the 2x minus 3/4 x² e to the 2x plus 3/4. Again, 3/4, 6/8 is the same as 3/4 x e to the 2x minus 3/8 e to the 2x plus a constant. Wow, it took less than a minute. If I don't talk, I don't explain, you just do it, it won't take a minute. But try to do that using the traditional way. U dv, so you do uv minus v du, the integral of v du. And then the integral of v du is still a product. So you'll have to divide it again. And you can see here we had to do that like 4 times. How long would that take? Plus, the potential of making a sign error when you subtract a negative term, and some people forget to do that, and you get the whole thing incorrectly. Okay, of course, if you have time, which defeats the purpose, but you can take the derivative of this function and see if you get the actual answer. Notice that some of them are products, so you have to apply the product rule. Okay, so that's another one. Let's pick a third. Let's pick one. For example, suppose I ask you, integrate natural log of x dx. And you'd say, but that's not a product. I say, yes, it's not, but I can make it a product. Say, what? How? I say, don't you see it? How do you make a natural log of x a product of 2 functions? Here's the trick. So if you have something that you know how to differentiate, but you don't know its integral and there is nothing multiplied by it, multiply it by 1. In fact, dx is 1 dx, right? And you would say then, here is the derivative, here is the integral, that's natural log of x, and that's 1. So the derivative of natural log of x, we said it's 1 over x. The integral of 1 is x. And like what we did here, we have to stop there. There is no reason to keep moving and make that x² over 2, and this is negative 1 over x². It doesn't make any sense. So you stop here and you say, this times that positive, but there is nothing to multiply here, so I'm going to integrate the product of these two with the negative sign. So I get the answer equals x natural log of x minus the integral 1 over x times x is 1, so minus integral of dx. So the answer is x natural log of x minus x plus a constant. Nice? Okay. Let's pick one last example so we can see. I think I found one that is nice. Yeah, because that will show you a third. So the first problem we found is when you have multiple ways of substitution. It's too long. So we developed the tabular form. The second one is when the function is not multiplied by anything and I don't know how to integrate it. So I create a fictional function to multiply it by, which is not here, but this one was similar, is that there is no reason to keep differentiating and integrating. So I stop at one level and integrate the two parts that are at that level when they will become much easier than integrating the original functions. Okay, now the third one is, suppose I want to integrate, what do they have here? Cosine 3x times e to the negative x dx. Notice, we said if there is a function that eventually will disappear, I would make it u. The problem is if I keep differentiating these two functions ad nauseum, they will never go away. The cosine will become negative sine if I differentiate it, or positive sine if I integrate it. If I keep doing, I will get cosine sine, negative sine, and it keeps forever. Same thing with e to the negative x. Whether I integrate it or differentiate it, I get the same result, which is negative e to the negative x, and then positive e to the negative x, and then negative. So what do I do in recurring functions like that? We are going to play a game. And this game is, I'm going to, first of all, just to reduce the amount of writing, I'm going to call that I for integral. My integral is this. And then here, I don't have really a preference. It's your preference. Which part do I use as u and which part do I use as dv? It's up to you. I don't care. Okay, so let's try to do that. We are going to say d and I. We can do it two times, but I don't think it's, it matters. So I'm going to use cosine of 3x as the differentiable part and e to the negative x as the integral part. When I differentiate cosine 3x, I get negative 3 sine 3x. And when I integrate that, in fact, it doesn't matter whether you integrate it or differentiate it, you get the same thing, e to the negative x. And then I will do it again. Why again? Because I want the cosine to show up one more time. And you say, how would that help? Bear with me for a second. Negative 9 cosine 3x and e to the negative x. Here I will stop and say, okay, I'm going to multiply this by that, positive, this by that, negative, and then I'm going to integrate those positive. Did you see what I did? Okay, so I equals this times that. There is a negative sign, so I end up with negative cosine 3x e to the negative x. My negative times negative is positive, so plus 3 sine 3x e to the negative x. And then minus, notice here I integrate because they are at the same level, minus 9 times the integral of cosine 3x e to the negative x dx. Sorry, I ran out of space. But what is this integral without the negative 9? That's what we called I. Integral of cosine 3x e to the negative x dx. So now I can rewrite these two terms minus 9i. And like I did in algebra, I add 9i to both sides. And I will get 10i equals, I can factor the e to the negative x. So I get, if you want, you can write it as 3 sine 3x minus cosine 3x, the whole thing times e to the negative x. So finally, or plus a constant. You can write that since this is an integral. So my integral I is, you can divide each term by 10, or you can simply say 3 sine 3x minus cosine 3x times e to the negative x over 10 plus a constant. And you see this trick happens when none of these two functions will eventually disappear by differentiation, but they are easily integrated or differentiated. One of them is you can go through a cycle, cosine, negative cosine, sine. So once this happens, especially with trig functions, sine and cosine, and e to the negative x also, or e to any power, is very easily differentiated or integrated, and it stays a function of e to the x or e to the negative x. And I think this covers pretty much all the cases you will encounter in integrating by parts. As usual, I say, if you have any questions, please send me or write a comment in the comment sections if I missed something, or sometimes you do a math error when you work quickly. So if you found anything that doesn't make sense or you think it's not correct, just let me know, or it wasn't explained properly. I will get back to you as soon as I can. Thank you very much for your time, and hope to see you very soon. Okay, let me stop. Thanks.